Hi, everybody, and welcome to Astronomy on Tap. This week, we will continue our Astronomy on Chat interview series with John Barentine as we talk about the imposing threat of satellite mega constellations. John is the Director of Public Policy at the International Dark Skies Association in Tucson, Arizona, and has a deep commitment to helping increase the public understanding of science. He received his PhD from the University of Texas and has a research background in solar physics, galaxy evolution, and developing hardware used in various telescopes. John is also a member of the International Astronomical Union, a fellow of the Royal Astronomical Society, and a member of the American Astronomical Society's Committee on Light Pollution, Radio Interference, and Space Debris. So, John, thank you for joining Astronomy on Tap.
Hey, thanks for having me, Jacob. I really appreciate the opportunity.
Oh, yeah, we're glad to have you here. So to start off, can you describe what exactly is meant by the term science policy?
There's actually two things that are meant by that. We usually read the phrase science policy and people think that it means science for policy. So science as it informs the creation of policy, and that's one of the aspects. And of course, a lot of scientists that participate in policymaking process will be involved on that side, offering their sort of professional view to inform decision making. But there's a second aspect to it that is policy for science. And so in order to efficiently conduct science, since it's usually a public enterprise in many parts of the world, we need adequate policy inputs there. And that might be things anywhere from the way money is spent on science to things like ethics in investigations and things of that nature. So most scientists that work in this field are on the front end and they're advising the policymaking process, but we should also keep in mind that part of it is how is science guided as an enterprise in the interest of the public.
Okay. So there's a new potential problem on the horizon in astronomy with these satellite mega constellations that are being launched by various companies. Can you tell us what sort of issues these can impose on astronomy specifically?
Mm-hmm. And when you say on astronomy, I kind of look at the totality of it. And of course, I'm interested in how it impacts professional astronomy, but there are plenty of amateur astronomers and even landscape photographers who will be impacted by them. Mm-hmm. So we're looking at this more than just the direct impact to science, but on sort of astronomy in a very broadly defined sense. Mainly, it will affect optical and infrared astronomers with scattering of light or reflection of light from the sun. And that's going to be mostly around twilight, around sunrise and sunset. We won't have quite as much of a problem around midnight when these objects are in the shadow of the Earth. The radio astronomers have a different situation because the satellites are probably going to be transmitting pretty much continuously once they're up. And so we will have to worry about radio frequency interference for radio astronomy facilities. But on the optical infrared side, it will be about satellites sort of, trailing through exposures, possibly running right over top of your science target. And then that becomes very difficult to control when we're talking about the quantities of objects that are involved here. So if we're going to find a way to live with these satellite constellations, first of all, we're going to have to get them down to the point that they're not nearly as bright as they appear when the objects are first launched, but also understanding their orbits well enough that we can predict where they will be to a high level of precision at any instant in time so that observations can sort of be scheduled around them. And I should also mention that even with the quantities that we're talking about, this is mainly going to be an impact to wide field survey telescopes like the Vera Rubin, for example. The fields of view of most professional telescopes are small enough that odds are you will not encounter a satellite trail even in a long exposure. But if you're seeing a large volume of sky at one time, and you're for example, you're trying to find near Earth objects, which are most prominent around sunrise and sunset, that's prime time for these objects, and it potentially has a very big impact on those operations.
Okay, so there's already a lot of satellites in space. So why is it that these new ones are particularly troubling for astronomers?
Yeah, it's a great question, and one that we have been asked a number of times, because of course we're now 60 plus years into the satellite age. And so the notion of satellites impacting astronomy or views of the night sky is not a new issue. What is new that we're talking about here has to do with the quantities of objects that are in play. Right now, there are, in terms of functional objects, there are a couple of thousand things in orbit around the Earth. Many of those are in geostationary orbit, which that's fairly easy to avoid because they don't really move at all on the night sky, and the satellites kind of line up along the geostationary band.
So a geostationary orbit, that's where it's always facing the same side of the Earth as it orbits around, correct?
Right. So if you want to, as a communication satellite, for example, if you want to dwell over a certain part of the world, you can set the orbital parameters of the satellite such that its period of revolution around the Earth is exactly 24 hours. And so it appears to just sit still. And so there's a band across the sky that's near the celestial equator where all of the geostationary satellites appear to hang out. And so since they don't move, they're fairly easy to avoid. The ones that we're really concerned about are in low orbit, only a few hundred kilometers up. And those are the ones that are going to cross the entire night sky. They can be incredibly bright. People are familiar with seeing the International Space Station, for example, that's in a low orbit, and because of its size, it can be very bright. But again, we're in a world now where there are a few thousand of these with pretty well known orbits. And we're talking about increasing the number of them in low orbit by over an order of magnitude. I counted up somewhere in the vicinity of about 50,000 objects that were in proposed large satellite constellations in the next decade. Not all of those will go up. Some of the companies that are in this space are already struggling. There's a company called OneWeb that had launched about 70 objects in the past 18 months, and that company has just recently gone into bankruptcy. There's a lot of competition in the business, and it's very possible that not all of the companies that want to launch satellites are going to survive and be successful.
Okay. So you said that there could be potentially 50,000 of these. Over what sort of time scale? Is that 50,000 next year, next decade?
Right. They're not all going to go up at once, of course. They're being phased in groups, but it's determined by how many satellites do you need to provide the service. And in this case, the service is broadband internet with global coverage and low latency. So meaning that there's not a long lag in the time required to get the signal up to the satellite and then back to the ground. And for the customers that these companies want to serve, that latency issue is very important, which is why they're putting things in low orbit, because you could just put everything up in geostationary and you wouldn't have to have many thousands of objects. But the latency for geostationary orbit that's up around 20,000+ kilometers is sort of unacceptably long for providing internet. That's why they need so many of them. The constellation of satellites, for example, that SpaceX is putting up right now called StarLink, their estimate right now is that their final configuration will be near 30,000 objects. And that would be in order to provide a certain level of service. They can function on a lower number, but there will be a time on the order of about 5 years or so when they are launching new objects every couple of weeks, 60 at a time, in order to get to that ultimate number of about 30,000. So this is going to take the better part of a decade, but 20 or 10 years from now, we very well might see several tens of thousands more objects in orbit than are currently in orbit around the Earth.
So you mentioned some of the other areas of astronomy that could be impacted by this, like radio astronomy with radio interference. Can you describe how exactly that might work? Because I think it's easy to visualize a light streaking across the sky, but it's harder to visualize radio interference.
Very much so. Of course, the radio astronomy people are used to conceptualizing radio signals in a certain way, and so that they can see this very easily. But for those of us that are more accustomed to working in optical IR, it's a pretty different story. You can imagine if you're looking up into the night sky and you see a satellite, that it has a pattern over which it is reflecting that sunlight. It's reflecting it into some solid angle. Some part of the Earth is seeing it at one time. And it largely works the same way for radio, except it depends on what you're trying to do with that radio communication to the ground. And it might be a very highly targeted kind of approach to where you would have a narrow beam of radio energy back to the ground. Or if you're up in geostationary, you may be just trying to blast the whole disk of the planet, because if you're serving satellite television, for example, you have a very large footprint on the ground of receivers that are trying to get to your signal. Whereas it's a little bit more narrow if you're just communicating between one satellite serving internet and one ground station. They will have these ground stations that then distribute the signal on the surface. They're also talking about, some other companies, about serving telephone signals this way. There was a project some years ago called Iridium that some of your viewers may have heard of, that was to provide satellite telephone calls over the entire Earth. And there were concerns at that time about not only the sunlight being reflected off the satellites, but how they were going to transmit radio to the ground. There is an international framework for dealing with radio interference. They have to, work within certain frequency bands that are outside of those that are typically used for radio astronomy. There are certain controls on the intensity of the signals. If you have a satellite blasting radio to the ground and it happens to fly right over, say, Green Bank in the United States, where the NRAO has its big telescopes, the risk that you run is damage or destruction of radio astronomy equipment, because the signals are so much stronger than the astrophysical signals you're trying to detect. So there's been a lot of coordination for many years between the satellite operators that have radio communications to the ground and the radio astronomy community in order to ensure that that doesn't happen. And it, for the most part, has worked out fairly well. These new generation of satellites that are going up in these very large constellations, under the regulatory framework we have right now, they have to play that game as well. And they're coordinating their observations or their operations to coincide with what the radio astronomers are doing with their observations, so that they don't yield an unnecessarily large impact to them. What is new is all of this optical IR discussion that we've been having and the impacts there. That is something that's different. And again, it just goes back to the numbers.
Okay. So how have professional astronomers around the world responded to these new satellite mega constellations coming up?
Well, Jacob, as you might imagine, they were very nervous when the first round of StarLink Objects went up just about a year ago. The idea that when Starlink launches, the 60 objects per launch are initially very close to each other, and they travel along the same orbit in the sky. So you'll have many objects lined up. And over the span of about 2 months or so, they use these very low power ion thrusters to raise their orbits to their final location. It's just more cost effective and takes less fuel if you allow some time to do it. And eventually they're spread out over these orbital shells. So you'll have, one orbit around the Earth, and you're distributing these 60 objects along it. But eventually they're going to be all over the sky. And the astronomers were naturally very alarmed by that when they realized what the prospect was for their future. And some organizations, some of which I belong to, have been trying to do something about this problem. Mainly what they're trying to do is, first of all, understand it, to be able to predict what the impact is. So there have been people who do simulations of these objects in terms of their impacts on astronomy, so that the decisions and the requests of the satellite companies are being made on the basis of fact, and not on hysteria or the sense of, we expect there are going to be thousands of these things just sort of simultaneously crawling across the sky. They wanted to be able to state what the impacts are in a quantitative way. So the simulations have been very important. All of the major professional astronomy organizations in the world have been in dialogue with the satellite operators, which to date has largely been SpaceX, because that's a company that has launched the most objects so far. SpaceX has responded, taking some steps to try to change the design of the satellites to minimize the reflections. They're already working within the regulatory requirements on the radio side to ensure that they will not cause undue interference to radio telescopes, but mitigating the reflections of sunlight is a new kind of request that they've had to address. And that's an ongoing story right now. They're trying some different things, the engineers, to make some changes to the satellite design that will minimize the reflections so that they're not quite as bright. And the astronomers have been able to provide some concrete goals. And that's also work that is ongoing as we better understand what the impacts are, to be able to say, to a company, if you can get your objects down below a certain brightness, that will mitigate a certain percentage of the impact to our science. And the hope is right now, instead of resorting to legal means or anything like that, by working with a company like SpaceX, which so far has shown an interest in being proactive about this and listening to the concerns of the astronomers and trying to address them, what we hope will happen is that will establish a best practice in the design and operation of these satellites, so that companies that follow will feel, hopefully, obligated to take the same steps to ensure that their satellites are not going to create new problems for astronomy.
Okay. So, we've talked about the different potential problems that this can have on astronomy. But what about outside of astronomy, either professional or non-professional astronomy? Are there negative impacts of putting a whole bunch of satellites in space?
Certainly, one of the things that we're worried about is the potential for the creation of new space debris. And that's a very broad catch-all term that means everything from non-functional satellites to spent parts of rockets that are used to launch them, to actual debris that's created either through a process where active satellites will shed little bits of insulation and that sort of thing, to rare instances, but ones that have happened, where satellites have collided with each other in orbit. And of course, when that happens, they create thousands of pieces of debris. And from the ground, at the civilian capability level, we can track objects down to roughly the size of about a soccer ball in Earth orbit. We're told that the military has the capability of.
For our European listeners, he means a football.
I mean a football. Yes. Betraying my Americanness. Yes, the size. So think the size of a football. Yes. So we worry about all of those things because they all have the potential to reflect sunlight, down to those very small pieces of debris. So to use an example, one of the things that we're interested in astronomy right now are very faint and fast transient things. So gamma ray bursts, for example, are a great example of this, where an astrophysical event happens in a very distant galaxy, and suddenly you get this wave of light that then fades out, and it's faint, and you have to kind of catch it when it happens. And that looks a lot like the behavior if you have a piece of mylar insulation that has come up off a satellite that is slowly rotating about its own axis and just briefly catches the light of the sun and reflects it back to the ground. Literally a piece of insulation that's only centimeters wide could produce a reflection that a telescope would see, that the consequence of which is you would not know that was not a true astrophysical event. So that's kind of one thing that we're worried about with space debris. But beyond astronomy, of course, there's a risk to other operational satellites. There's a risk to science-based satellites in low orbit, such as the Hubble Space Telescope, for as long as it lasts. It's in that zone where it potentially could be the victim of a collision with space debris. So we worry about that. The operators of the large satellite constellations are taking this into account and are designing mechanisms by which, when one of their satellites is no longer useful anymore, it can be deliberately deorbited. And there's sort of a best practice for that, so that you don't end up with a graveyard of disused satellites at some orbit that just become targets to generate more space debris. So that's one thing. Beyond professional astronomy, this is a special interest to my organization because we're about the protection of the night sky very generally. And that affects people who are not professional astronomers, but are everything from very serious amateur astronomers that do a lot of photography to just casual stargazers. And because the night sky as a cultural object is something that's meaningful to a lot of people on Earth, of course, we're concerned about the idea that our view of the night sky would be very severely impacted by a lot of these new artificial objects, which kind of become distracting in certain numbers. And so instead of a nice view of the Milky Way from a dark site, your attention is diverted by all of these things that are constantly moving. So for our purposes in that, one of our main goals is that we would like to see these objects be below the brightness that is visible to the naked eye. And we would like that to happen fairly soon after launch. And that's one of the things that SpaceX has committed to publicly, is that within a week of launch, these objects will not be visible to the naked eye. So you'll only see them immediately after they were going up, or the ones that are about to come down through the deorbit process. And consequently, we would like them to be the way they are now, which is a fairly unusual experience for most people. You might see one or two satellites that are bright enough to be visible to the naked eye an hour if you're in an average sized city. It's not something that's very distracting. So we've asked them to take that into consideration. And then to also be very transparent about things like launch schedules, providing orbital information about the satellites as quickly as they know it to the astronomers, so that we can better kind of dodge the satellites when we're making observations. I think if we can get them to agree to do those things, and if they can do them, then this problem might be largely contained, and we can coexist. And that's something my organization has been upfront about from the beginning. We're not opposed to satellites, and I don't think astronomers should necessarily be opposed to satellites, but we should be insistent that the operators are putting these things up in a responsible way, bringing them down responsibly at their end of life, and ensuring that they have the very least impact possible, not only to professional science observations, but also to those casual stargazers as well.
Okay. So it sounds like there's some work that's being done currently between these organizations and astronomers, like that are running simulations and talking about what they need. So from a policy perspective, like what still needs to be done to mitigate all of the potential future impacts?
Man, that's something I've been thinking a lot about in the past year since the first Starlink launch, and have gotten a lot of questions to that effect, and had to learn a lot in a short period of time to be able to answer questions of this nature. The short answer to your question is our international policy framework for governing activities in space needs modernized in a very desperate way. And I say modernized because what governs these activities now is something called the Outer Space Treaty of 1967, to which most of the countries of the world are party. That was crafted by the United Nations in the run-up to when the astronauts went to the moon. When we were concerned about, who is going to be the first to get to the moon? Will it be the Soviets or the Americans? And the thinking was somebody was about to make a territorial claim to the moon, or part of it. And so that's much of what this policy framework deals with. It deals with the commercial activities, repatriation of materials, like if you mined important metals on an asteroid or on the moon, how would that be dealt with? And it really doesn't talk about things like communication satellites. So I would say that the problem right now is that the framework that we've been using for more than 50 years is really inadequate for the issue of these large constellations of satellites. And one of the things that it definitely does not deal with is the impact to astronomy or the night sky as a cultural object. And that's something that a modernization of space policy would help address. It won't do anything about the situation that we find ourselves in now. And it also leaves up to the individual member states that signed the treaty to regulate this through their own domestic law. And right now, one of the criticisms of the US is that we're in a time in our history where our governance is very permissive towards commercial activities generally, I would say. And so there's not very much interest in our country to add new regulation to this space. So if we just leave it up to the individual countries, I don't know that that's really going to take us where we want to go. But if we in the United States just dealt with this issue on our own with policy, there's a very good chance that the operators that didn't like that would just move to another country to do their launches, because the Outer Space Treaty makes the country of launch responsible for the results of the activity. And that's probably something that needs to change in the long run. So the short answer is there's really not much that can be done under the current existing policy framework. Or, some of the astronomers have asked, can't we bring a lawsuit against the satellite operators, for example? And that doesn't look very good either under the current situation. So I think, and I hope that this will be a wake-up call to enough people looking into the future to say, the world has changed. The human uses of space are rapidly evolving. This will affect astronomy in the future one way or another. And we should decide now what changes we want to make in order to ensure that in the future, we have a better framework to guide the evolution of these activities. That's what it ultimately amounts to.
Okay. Well, thank you very much for sitting down with us and discussing this issue. I learned a whole lot. So if nobody else got anything out of this, I sure got a lot out of it. So really appreciate you coming on and talking with us.
Happy to do so. And again, thank you for the invitation.
Yeah, thanks. We'll talk to you later.
Okay.